Many of the quantities used for modeling the immediate state or dynamics of change of a system in physics are vectors. In this video, we will describe vectors, vector spaces, and basis sets. A vector is an arrow. The vector v is denoted with an arrow accent. A vector is the location of the arrow's head in relation to the arrow's tail, and the position of the head in relation to the tail is expressed in terms of a magnitude, meaning a length, and a direction, or if you would like, an angle. In addition to the vector v, consider other examples of vectors w, x, y, and z. We said that a vector was defined as the location of an arrow's head in relation to its tail. Even though the arrows in this animation are jiggling, not one single vector is changing. None of the arrows is changing directional orientation. None of the arrows is changing length. The position of each arrowhead remains unchanged in relation to its corresponding tail. These vectors are not changed even when the positions in the page where they are drawn are changed. Place the tail of vector w at the head of vector v. The vector connecting the tail of v to the head of w is denoted vector v plus vector w, and called the resultant of adding w to v. Notice that we obtain the same resultant if we reverse the order of addition. Head-to-tail addition of vectors v and w produced a resultant vector not already belonging to our original set of vectors. The resultant v plus w does not equal in direction and length any of the other vectors already illustrated. Extending vector y produces a vector that equals vector z in direction and length. In this example, we doubled the length of vector y. This scaling of y produced 2y, which equals z, a vector belonging to our original set of vectors. Depending on the set of vectors being initially considered, some examples of scalar multiplication might generate vectors already in the set of interest, while other examples of scalar multiplication might generate vectors not yet in the set of interest. Also, depending on the set of vectors initially being considered, some examples of vector addition might generate vectors already in the set of interest, while other examples of vector addition might not. A vector space is basically a set of vectors that is closed under scaling and vector addition. This is to say that neither scaling nor vector addition produces a result not already included in the so-called space. A vector space is a set of vectors that is closed under scaling and vector addition. Consider a set of vectors b1, b2, and so on up to bd. For example, here's a yellow vector and an orange vector, so d equals 2. A linear combination is an addition of vectors that have individually been pre-stretched by the scaling factors c1, c2, and so on up through cd. Here is one linear combination with an extended version of the yellow vector. Here is a linear combination with a stretched out version of the orange vector. Here is a version with a stretched out and inverted version of the yellow vector. Multiplying by a negative scaling factor reverses the direction of a vector. We have illustrated merely 3 examples of linear combinations of the yellow and orange vectors. Consider the collection of vectors that is the enumeration of all possible linear combinations of the yellow and orange vectors. We will now argue that this set is a vector space by thinking about scalar multiplication and vector addition. Scalar lengthening of this pink vector can be visualized by scalar multiplication of the yellow and orange pieces from which it was constructed. The dashed yellow and orange vectors are scaled versions of the original yellow and orange vectors at the left-hand side of the slide, so the enlarged pink vector is obviously still a linear combination of the original yellow and orange vectors. To the pink vector we have just enlarged, let's add, for example, a small version of this pink vector. Rearranging some dashed yellow and orange pieces, we can see that the resultant of head-to-tail addition of these pink vectors is still a linear combination of the original yellow and orange vectors. We used a set of vectors to prescribe a vector space. The set of linear combinations of a set of vectors is itself a vector space. We generated a vector space from two vectors using the idea of linear combination. We can also start with not two, but only one vector. Here is one pink arrow constructed by multiplying the original yellow arrow by, in this case, the factor 1, and adding it to, well, there is nothing else to add it to because we initially listed only one vector. Here are additional examples where the scale factor has been made larger or negative. While we can make lots of vectors by playing with the lengths of arrows or by reversing orientation, which again is multiplication by -1, the set of pink arrows generated by applying the idea of linear combinations to the single yellow vector is in a sense simpler than the set of pink arrows generated starting with the two vectors. The pink arrows generated from the yellow and orange vectors have the ability to point in a variety of directions in the page. Can we generate a more complicated collection of pink arrows by starting with these 3 arrows instead of only 2? If the yellow, orange, and brown arrows all lie in the two-dimensional plane of the page, then the pink arrows generated as linear combinations will also remain confined to the page, affording them no freedom not already enjoyed by the pink arrows generated through linear combination of the two vectors in the middle row. Both sets of pink vectors explore the array of compass directions that can be represented within the plane of a page. Both collections of pink arrows describe the same vector space V. These two vectors form a basis, or you can say basis set, for the vector space V, meaning not only that they suffice to prescribe the vector space V through linear combination, but additionally that they will fail to prescribe the vector space V upon the removal of any vector. If you remove the orange basis vector, you get the distinct vector space in the upper row. Removing instead the yellow basis vector would also restrict the directions that the pink arrows could explore. The dimensionality of a vector space is the number of vectors in a basis for it, so the vector space V is two-dimensional. A basis set defines a vector space. A basis set can be visualized as defining a coordinate system. Copy the yellow and orange vectors here. This pink arrow is an example of a linear combination made using yellow and orange. This pink arrow is the linear combination constructed by doubling the length of the yellow basis vector and leaving the length of the original orange vector unchanged. This pink arrow is made using 3 copies of yellow and -1 copies of orange. Other pink arrows can be accessed on this grid. A vector V can be described as a yellow part and an orange part. A vector V is a number of copies V1 of basis vector B1 and a number of copies V2 of basis vector B2. V1 and V2 can be thought of as coordinates like x and y from the more familiar Cartesian grid. Specifying V1 and V2 specifies a location on the yellow-orange grid. Basis vectors B1 and B2 are not the only vectors that can provide a coordinate system for identifying positions in the plane of the page. Vectors beta1 and beta2 also serve as a basis. A generic vector V can be expressed as a cyan part and a blue part. V yellow 1 and V cyan 1 are colored distinctly to guard against mistaking these coefficients for being equal. We have colored the V2s in the same way. We have just shown that a basis set can provide a coordinate grid for specifying vectors in a vector space. In the next video, we discuss operators. Operators are pieces of machinery that produce a vector when given a vector. We will learn that basis sets can provide a concrete representation of the action of operators.